Right now, as you're watching this video, there's a cosmic giant lurking in the shadows of our solar system. This mysterious world is roughly 10 times more massive than our entire planet, yet it remains completely invisible to every telescope we've ever pointed toward the stars. How do we know it exists? Because it's secretly controlling distant worlds like a cosmic puppeteer, making them dance in perfect formation across the frozen wasteland beyond Neptune. Scientists have uncovered mathematical fingerprints that prove this hidden planet is real. Desperate astronomers are currently sweeping through 20,000 square degrees of empty black space, hunting for the most elusive discovery in modern astronomy. When they find it, everything we thought we knew about planetary formation will need to be completely rewritten. If you're ready to dive into the greatest cosmic mystery of our time, smash that like button and hit subscribe, because we're about to explore the incredible detective story that revealed this invisible world. Let's begin this mind-blowing journey. 4 billion miles away from our sun, something absolutely bizarre is happening in the outer reaches of our solar system. Deep within the Kuiper belt, where ancient chunks of ice and rock drift through the endless cosmic darkness, 6 enormous objects are completely defying the laws of physics as we understand them. These aren't ordinary space rocks we're talking about. Each one towers larger than mountains, with some stretching bigger than entire American states. Yet they're all performing an impossible cosmic ballet that has left astronomers completely baffled. Imagine walking into a classroom and discovering that 6 students have mysteriously arranged their desks at identical strange angles, all pointing toward the exact same bizarre direction. Your first thought would be that someone deliberately moved them that way. Something or someone had to orchestrate this arrangement. That's precisely what scientists discovered when they analyzed these distant cosmic wanderers. Objects with names like Sedna, Biden, and the cryptically labeled 2012 VP 113 follow orbital paths so incredibly stretched and twisted that they resemble giant cosmic eggs lying sideways in space. But here's where things get absolutely mind-boggling. Every single one of these massive objects tilts in virtually the same direction. The mathematical probability of this occurring randomly equals your chances of flipping a coin and landing heads 20 consecutive times. We're looking at odds of roughly 1 in 64. This isn't coincidence. This is undeniable proof that something is manipulating them. These rebellious worlds exist in a realm so unimaginably distant that sunlight requires over 6 hours to travel there. From their perspective, our sun appears as nothing more than another bright star twinkling in the cosmic void. There's no warmth, no heat, just the bone-chilling cold of infinite space where temperatures plunge hundreds of degrees below freezing. Yet despite this incredible isolation, something with tremendous gravitational power is orchestrating their movements with invisible force. Picture a shepherd guiding a flock of sheep across a vast meadow. You might not see the shepherd from a distance, but watching the sheep move in perfect unison tells you someone is directing their path. These distant worlds are the sheep, responding to commands from an unseen cosmic shepherd. What makes this phenomenon even more extraordinary is how dramatically these objects differ from everything else in our solar system. Most celestial bodies orbit our sun like race cars on a track, staying roughly within the same flat plane we call the ecliptic. It's an orderly system where planets, asteroids, and comets generally follow predictable circular paths. But these cosmic rebels have thrown that rulebook out the window. They're dramatically tilted upward and outward from the normal orbital plane, as if they're following instructions written by an entirely different gravitational authority. Their paths stretch so far into space that they practically abandon the solar system altogether, before eventually swooping back toward the sun in impossibly elongated journeys. Scientists have dubbed this the clustering problem, and it's keeping astronomers awake at night. When you plot these orbital paths on a 3-dimensional map of space, they all aim toward the same mysterious region beyond Neptune. It's as if something absolutely massive is stationed out there in the darkness, something with enough gravitational muscle to control worlds the size of Texas from distances measured in billions of miles. For generations, astronomers confidently believed they had catalogued the major players in our solar system. We had identified the 4 gas giants, mapped Pluto and its neighbors, and assumed the outer regions contained nothing but scattered debris and cosmic leftovers from the solar system's violent birth 4.5 billion years ago. We were spectacularly wrong. These orbital revolutionaries are actually cosmic messengers, delivering urgent news from the darkest corners of our neighborhood. They're telling us that our solar system has been harboring an incredible secret since the very beginning of planetary formation. Hidden beyond the reach of our most powerful instruments lies evidence of processes and forces we never imagined existed. Think about the implications for a moment. These objects aren't small pebbles being nudged by minor gravitational influences. We're talking about worlds containing billions of tons of rock and ice, some with diameters stretching hundreds of miles. The amount of gravitational force required to synchronize their movements across such vast distances is absolutely staggering. The mysterious puppet master controlling them must possess incredible mass and occupy a very specific location in space. It can't be too close, or we would have spotted it by now. It can't be too far away, or its gravitational influence would be too weak to affect these distant worlds. It must exist in a precise sweet spot where it can exert maximum control while remaining completely invisible to our detection methods. This hidden world represents more than just another planet waiting to be discovered. It's a missing piece in the puzzle of how solar systems form and evolve. Finding it could revolutionize our understanding of planetary migration, gravitational dynamics, and the chaotic early history that shaped our cosmic neighborhood. The evidence is mounting with each new discovery in the outer solar system. Every additional rebel object we find strengthens the case for this invisible giant. The mathematical signatures are becoming impossible to ignore, painting a picture of gravitational architecture that demands explanation. But the mystery is just beginning to unfold, and the most incredible part of this story is yet to come. Space stretches infinitely in every direction, and random coincidences happen all the time across the cosmic void. When astronomers first noticed a few distant objects clustering together beyond Neptune, many dismissed it as nothing more than statistical noise. But as more mysterious worlds were discovered lurking in the outer darkness, the pattern transformed from curious coincidence into undeniable evidence of something extraordinary. This wasn't random chance anymore. This was proof of a cosmic conspiracy orchestrated by forces beyond our comprehension. The smoking gun that convinced skeptical scientists lies buried in something called the argument of perihelion. Don't let the technical terminology scare you away, because this concept is actually beautifully simple. This represents the precise point where each object reaches its closest approach to our Sun during its marathon orbital journey. Think of it as the bottom of the most extreme cosmic roller coaster ever constructed. The exact moment where each distant world achieves maximum velocity before climbing back into the frozen outer darkness. Here's what makes this absolutely mind-blowing. For 6 major objects discovered beyond Neptune's orbit, these closest approach points cluster within approximately 60 degrees of each other across the sky. Picture looking at a traditional clock face hanging on your wall. If one mysterious object reaches its closest solar approach at the 12 o'clock position, all the other conspirators cluster between 10 o'clock and 2 o'clock. The mathematical odds of this happening through pure random chance equal your probability of winning the lottery twice during the same week. We're talking about astronomical improbabilities that should never occur in a universe governed by chaos and coincidence. But this gravitational conspiracy extends far deeper than simple directional clustering. These rebellious worlds aren't just pointing toward the same region of space, they're also tilted away from the main orbital plane of our solar system by remarkably similar amounts, as if they're all following instructions from the same cosmic architect. Most planets in our solar system orbit the Sun like race cars speeding around a perfectly flat track, staying within just a few degrees of the same level throughout their journeys. But these distant revolutionaries are tilted upward by 15 to 30 degrees, as if they're all traveling along the same mysteriously angled highway leading into the depths of space. The object called Biden provides the perfect example of this impossible precision. This world measures roughly the same size as Pluto and requires 550 years to complete a single orbital lap around our Sun. At its most distant point, Biden ventures outward to nearly 150 times Earth's distance from our solar center. That's so incredibly far that radio signals transmitted from Earth would require over 20 hours to reach this frozen world. Yet, Biden's orbital characteristics align precisely with the other cosmic conspirators. Its orbital plane, its tilt angle, its direction of motion, every measurable parameter matches the pattern predicted by Planet 9's invisible gravitational influence with shocking accuracy. Then there's the mysteriously designated 2012 VP 113, discovered by the same research team that identified Biden. This object follows an even more extreme orbital path, swinging outward to over 200 times Earth's distance from the Sun. Its complete orbital journey requires 4,000 years to finish. Yet it too follows the same mysterious alignment with mathematical precision that defies explanation. The most compelling evidence emerged from sophisticated computer simulations run by teams of astronomers around the world. When researchers remove Planet 9 from their digital models and allow the solar system to evolve naturally over millions of years, something fascinating happens. The clustering pattern completely disappears within just a few million years. The distant objects scatter randomly across the sky, following the chaotic, unpredictable paths you'd expect from worlds influenced only by our Sun and the known planets. But when scientists add Planet 9 back into their simulations, inserting a world 10 times Earth's mass orbiting at the predicted distance, the clustering reappears like magic. The previously scattered objects gradually migrate back into the same tilted, aligned configuration we observe in reality today. It's like watching cosmic destiny unfold in fast-forward motion. The conspiracy extends beyond orbital alignment into the physical characteristics of these mysterious worlds. These objects display similar colors and compositions, suggesting they might have originated in the same region of the early solar system, before being scattered by Planet 9's overwhelming gravitational influence billions of years ago. 6 cosmic witnesses, all providing identical testimony about the presence of something massive lurking in the shadows of our solar neighborhood. But the mathematical evidence was about to become even more convincing and absolutely overwhelming. Numbers never lie, and in the case of Planet 9, they're screaming that something colossal is pulling gravitational strings across interplanetary space. When astronomers want to prove something exists beyond reasonable doubt, they turn to the cold, objective language of statistics. This mathematical approach strips away wishful thinking, personal bias, and romantic speculation, revealing only truth. The statistical case for Planet 9 borders on mathematical certainty. The clustering of distant objects isn't just unusual or noteworthy, it's mathematically impossible without the influence of an external gravitational force. Imagine flipping 6 coins simultaneously and watching them all land heads up. That result would definitely surprise you, but it happens naturally about once in every 64 attempts. Now imagine flipping those same 6 coins 100 times in a row and watching them land heads up every single time, without exception. That's not luck anymore. That's undeniable evidence of loaded coins or deliberate manipulation. The orbital alignment of these distant worlds represents odds far worse than any loaded coin scenario. When astronomer Scott Shepard calculated the probability of 6 objects randomly clustering exactly as they do, he discovered chances of approximately 1 in 4,000. Those odds alone would convince most scientists, but that calculation represented only the beginning of the statistical avalanche. As more mysterious objects were discovered hiding in the outer solar system, the evidence became absolutely overwhelming. The object designated 2014 SR 339 follows the same tilted, elongated orbital pattern as all the others. So does 2013 RF 98. Each new discovery that perfectly fits the predicted pattern makes random chance exponentially less believable. Think of it like investigating a crime scene where 6 independent witnesses provide identical testimony down to the smallest, most specific details. Either they're all participating in an impossibly coordinated lie, or they're all telling the absolute truth about something they genuinely witnessed. The statistical analysis extends far beyond simple directional clustering. These objects also demonstrate what astronomers call longitude of perihelion alignment, which describes the specific direction in space where each object makes its closest approach to our Sun. For all 6 major objects, this direction points toward the same narrow wedge of sky with precision that defies coincidence. But here's where this cosmic mystery becomes even more fascinating and bizarre. These distant worlds aren't just aligned with Planet 9's predicted position, they're anti-aligned, clustering on the completely opposite side of our solar system from where Planet 9 should be orbiting. It's as if they're all fleeing from something terrifying, running away in perfect formation. This discovery continues to strengthen the case for our solar system's most elusive resident. The mathematical evidence supporting Planet 9's existence has reached a critical tipping point, where denying this hidden world's reality requires explaining away coincidences that completely strain scientific credibility. But successfully identifying this cosmic puppet master represents only half of the incredible mystery we're unraveling. Understanding exactly what kind of world could wield such tremendous gravitational power across billions of miles constitutes the other half of this mind-bending puzzle. Planet 9 isn't just expertly hiding its precise location from our most powerful telescopes. It's also concealing its fundamental identity and true nature from human understanding. The gravitational evidence screams that something absolutely massive is lurking in the frozen darkness beyond Neptune's orbit. But determining exactly what that mysterious something actually represents requires detective work that pushes the absolute boundaries of modern planetary science. Here's the burning question that keeps scientists awake at night. Is Planet 9 a super-Earth, essentially a rocky world built exactly like our home planet, but scaled up to absolutely massive proportions? Or could it be a mini Neptune, representing a smaller version of our solar system's ice giants, complete with thick atmospheric envelopes and exotic chemical compositions that exist nowhere else in our immediate cosmic neighborhood? The mass calculations are relatively straightforward when you examine the gravitational evidence. To shepherd distant objects across interplanetary space the way Planet 9 accomplishes this feat, it must weigh at least 5 times more than our entire planet, and probably closer to 10 times Earth's total mass. That measurement places it squarely within the category that astronomers call super-Earths, representing worlds that are significantly bigger than our planet, but considerably smaller than Neptune. But mass measurements alone don't reveal the complete story about Planet 9's true nature. A world weighing 10 times Earth's mass could represent several completely different scenarios. It might be an incredibly dense, rocky super-Earth measuring approximately twice our planet's diameter, with solid surface materials compressed under tremendous gravitational pressure. Alternatively, it could be what scientists call a fluffy mini Neptune, measuring 3 times Earth's size but filled primarily with water, methane, and hydrogen, rather than solid rock. This fundamental difference matters enormously, because it tells us where Planet 9 originally came from, and how it managed to reach its current mysterious location in the outer solar system. Think of this challenge like trying to identify a person based solely on their shadow cast against a wall. You can determine they're tall from the shadow's length, but you can't tell whether they're a professional basketball player or simply someone wearing platform shoes. Planet 9's gravitational shadow clearly reveals its approximate mass, but provides no direct information about its internal composition or surface characteristics. The rocky super-Earth scenario paints Planet 9 as a world fundamentally built like Earth, but scaled up to dramatic proportions that dwarf our home planet. Its surface would represent a completely frozen wasteland composed of rock and ice, with surface temperatures permanently hovering around -400 degrees Fahrenheit. Any atmosphere that might have existed would be frozen solid on the surface, creating landscape features unlike anything humans have ever witnessed. This would be an alien world where carbon dioxide snow falls continuously like volcanic ash from the perpetually dark sky, and where the ground's surface is compressed hard enough to shatter diamonds on contact. Imagine the most extreme Arctic conditions you've ever experienced, then multiply that harshness by factors that make Earth's polar regions seem tropical by comparison. The mini Neptune scenario presents a far more exotic and fascinating possibility. This version of Planet 9 would be wrapped in an incredibly thick envelope of hydrogen and helium gases, perhaps concealing deeper layers composed of water and ammonia ice beneath its atmospheric shell. Its core might contain rocky materials, but the majority of its bulk would consist of gas and ice rather than solid matter. This represents a world where the atmosphere itself outweighs entire continents on Earth, creating pressure conditions and chemical environments that exist nowhere else in our solar system. Recent scientific studies increasingly suggest that Planet 9 probably resembles the mini-Neptune model more closely than the rocky super-Earth scenario. Sophisticated computer simulations of planetary formation processes demonstrate that rocky super-Earths encounter serious difficulties growing beyond approximately 5 Earth masses when they form in the outer regions of solar systems. The simple truth is that there isn't enough solid material available in the outer solar system to construct truly massive rocky worlds through normal planetary formation processes. But mini-Neptunes can grow significantly larger by directly accumulating gas from the solar nebula, which represents the disk of hydrogen and helium that surrounded our young sun during the early stages of solar system formation. If Planet 9 truly represents a mini-Neptune, it must have formed during the first few million years of our solar system's turbulent history, when gas was still abundantly available for planetary accumulation processes. The size debate carries profound implications for Planet 9's brightness and detectability characteristics. A rocky super-Earth would appear extremely dark to our telescopes, reflecting less than 5% of the minimal sunlight that manages to reach its distant location. But a mini-Neptune might feature clouds or atmospheric haze layers that could make it slightly brighter and potentially easier to detect with advanced astronomical instruments. The temperature differences between these scenarios also matter significantly for detection strategies. A rocky world loses internal heat very slowly, staying relatively warm for billions of years through continuous radioactive decay, processes occurring within its core. But a mini-Neptune cools much faster, potentially making it detectable through infrared light observations as it radiates away its stored internal heat into the cosmic void. Understanding Planet 9's true nature could completely revolutionize our fundamental knowledge of planetary formation processes throughout the universe. But before we can achieve that breakthrough, we need to solve an even bigger and more shocking mystery. How did something so incredibly massive manage to end up so impossibly far from its probable birthplace? Planet 9 might actually represent an alien world that our sun successfully stole from another star system, approximately 4.5 billion years ago. Back then, our solar system wasn't the lonely cosmic island it appears to be today. Our sun was born within a stellar nursery, representing a crowded galactic neighborhood where hundreds of young stars formed simultaneously from the same giant cloud of gas and dust. In that chaotic cosmic daycare center, planetary theft wasn't just theoretically possible, it was absolutely inevitable. Picture a cosmic version of musical chairs, except instead of competing for chairs, young stars are actively stealing planets from each other through gravitational interactions. Young stars in dense clusters regularly pass within a few hundred times Earth's distance from each other. That might sound incredibly far, but in cosmic terms, it represents close enough proximity for successful gravitational hijacking operations. Computer simulations of these early stellar encounters reveal something absolutely shocking about planetary system evolution. When two star systems pass close together during these cosmic encounters, their outer planets get tossed around like cosmic ping-pong balls in a gravitational tournament. Some planets get ejected entirely from their home systems, becoming rogue worlds that drift alone through interstellar space for eternity. Others get captured by passing stars, becoming permanent members of completely new stellar families through gravitational adoption processes. The mathematical models work perfectly for Planet 9's current situation and predicted characteristics. If we ever successfully locate this mysterious world and manage to study its detailed composition, we might discover chemical elements and isotope ratios that don't match anything else found throughout our solar system. It would be like encountering a person speaking with a distinctly foreign accent in your hometown, providing clear, undeniable evidence of distant origins and exotic heritage. The planetary capture process that brought Planet 9 to our solar system wouldn't have been gentle or gradual. This world would have been violently yanked away from its birth star with tremendous gravitational force, probably losing any moons it might have possessed during the chaotic transition process. Planet 9 would have tumbled helplessly through the empty void of interstellar space for millions of years, before eventually settling into its current orbital pattern around our sun. But the rogue planet theory faces one absolutely major challenge that keeps scientists debating its validity. Successfully capturing a planet from another star system is incredibly difficult to accomplish. The gravitational dance between passing star systems must be perfectly choreographed with precise speeds, angles, and timing that border on the miraculous. Most close encounters between star systems result in planets being violently ejected into interstellar space rather than captured by the visiting star. Recent scientific studies suggest that only approximately 1 in every 1,000 close stellar encounters results in successful planetary capture. That statistical reality makes Planet 9 either incredibly lucky or evidence that our early solar system experienced far more stellar encounters than we previously believed possible. Either way, Planet 9 might represent our solar system's most exotic immigrant, a mysterious world that traveled between distant stars for eons before finally calling our sun home. But there's an even stranger and more mind-bending possibility lurking in the shadows of scientific speculation. What if Planet 9 isn't actually a conventional planet at all? While most astronomers focus their powerful telescopes on finding a massive world beyond Neptune's orbit, a few maverick scientists are seriously exploring possibilities that sound like pure science fiction. The gravitational evidence remains rock solid and undeniable. Something with significant mass is definitely influencing distant objects in the outer solar system. But that mysterious something might be far stranger than any conventional planet we've ever discovered. The primordial black hole theory transforms the search for Planet 9 into a hunt for one of the universe's most exotic and terrifying objects. These aren't the monster black holes that devour entire stars and solar systems in spectacular cosmic violence. Primordial black holes are microscopic remnants from the universe's violent birth, compressed to densities that completely defy human imagination and understanding. A primordial black hole containing the mass of 10 Earths would measure smaller than a bowling ball, yet it would warp spacetime exactly like Planet 9 is predicted to accomplish. It would shepherd distant objects with identical gravitational precision, creating the same clustering patterns that originally convinced astronomers a 9th planet must exist. The concept isn't as crazy as it initially sounds to most people. Leading cosmologists believe primordial black holes formed during the first fraction of a second following the Big Bang, when extreme density fluctuations in the early universe collapsed under their own overwhelming gravity. These ancient relics could be scattered randomly throughout our galaxy, remaining completely invisible until their gravitational effects accidentally give away their hidden locations. Finding a primordial black hole would be nearly impossible using current astronomical technology. Unlike conventional planets, black holes don't reflect light from their surfaces. They don't emit detectable heat signatures. They remain essentially invisible except for their gravitational influence on surrounding objects, which is exactly what we're observing in the outer solar system. But the primordial black hole theory faces serious scientific challenges. These objects are extremely rare throughout the universe, and the odds of one being captured by our solar system are astronomically small. It would be like winning the cosmic lottery with a ticket you didn't even know you had purchased. The dark matter hypothesis offers an even more exotic and fascinating explanation for the mysterious gravitational effects. What if the gravitational phenomena currently attributed to Planet 9 are actually caused by an unusual concentration of dark matter? This represents the mysterious invisible substance that comprises most of the universe's mass, but interacts with normal matter only through gravitational forces. Dark matter typically spreads itself thinly throughout space, remaining invisible and completely undetectable, except through its gravitational effects on visible matter that we can observe. But under certain rare conditions, dark matter can clump together into dense halos that behave exactly like massive objects with planetary characteristics. A dark matter halo containing the mass of several Earths could theoretically produce the same gravitational shepherding effects that we attribute to Planet 9's influence. The particular appeal of the dark matter theory lies in how it explains why Planet 9 has proven so incredibly difficult to locate despite years of intensive searching. Dark matter doesn't emit or reflect light in any detectable way, making it completely invisible to even our most powerful telescopes. It would represent the ultimate cosmic hide-and-seek champion, something possessing enormous gravitational influence, but maintaining zero visibility to human detection methods. Some scientists have proposed even more exotic alternative explanations that push the boundaries of known physics. Could the gravitational anomalies be caused by modifications to Einstein's fundamental theory of gravity that only become apparent at extreme distances? Or could they result from mysterious interactions with extra dimensions that exist beyond our normal three-dimensional space? These alternative theories share one significant common problem. They're almost impossible to test or verify using current technological capabilities. Unlike a conventional planet, which would eventually appear in sufficiently powerful telescopes, primordial black holes and dark matter concentrations remain stubbornly invisible to direct observation. The broader scientific community remains largely skeptical of these exotic alternative explanations, not because they're theoretically impossible, but because they require invoking rare and poorly understood phenomena to explain observations that a conventional planet explains perfectly well using established physics. But until someone actually locates and photographs Planet 9, these alternative explanations continue to lurk in the shadows of scientific possibility, waiting to surprise us all. Meanwhile, the search itself has evolved into a high-tech treasure hunt involving the most powerful and sophisticated telescopes ever constructed on Earth. Finding Planet 9 has become the ultimate test of human ingenuity, technological precision, and astronomical determination. From the volcanic peaks of Hawaii to the bone-dry deserts of Chile, the world's most advanced telescopes have turned their incredibly sensitive electronic eyes toward the outer darkness, hoping to capture the first precious photons of light reflected from our solar system's most elusive world. This isn't just conventional astronomy anymore. This represents technological warfare against the cosmic darkness itself. The Subaru telescope stationed on Mauna Kea leads this incredible charge with its revolutionary hyper-suprime cam, a camera so extraordinarily sensitive it could detect a single candle flame burning on the moon's surface. This mechanical eye captures detailed images covering an area of sky equivalent to 9 full moons in a single exposure. But even with that enormous field of view, completely mapping the entire Planet 9 search zone requires thousands of individual exposures taken over many years. Each night of clear weather represents a precious and irreplaceable opportunity. Telescope time costs more than gold, with astronomers from around the world competing fiercely for just a few hours of observation time. This cosmic detective story continues to unfold as humanity's greatest technological achievement. While the Dark Energy Survey's primary mission focuses on studying dark energy in distant galaxies billions of light-years away, the survey data contains an absolutely incredible treasure trove of information about moving objects right here in our own solar system. Think of this process like creating a massive time-lapse movie of the entire night sky, where every frame captures millions of stars and cosmic objects. Objects that appear in multiple images, but shift their positions between exposures get automatically flagged by sophisticated computer programs as potential planets or asteroids. The monumental challenge lies in distinguishing Planet 9, which would be moving incredibly slowly at the very edge of our solar system, from the millions of much faster-moving asteroids that populate the inner regions around Mars and Jupiter. The Catalina Sky Survey in Arizona has completely transformed itself into a dedicated Planet 9 hunting machine, using a pair of powerful telescopes to systematically scan nearly the entire northern sky every single month. Their supercomputers process over 1 million individual images every year, using advanced algorithms to identify absolutely anything that moves against the seemingly static background of distant stars. Each promising candidate that emerges from this digital sifting process triggers immediate follow-up observations designed to determine whether the object represents a newly discovered asteroid, a previously known space rock, or possibly the astronomical discovery of the century. Modern telescope surveys generate absolutely staggering amounts of data that would have been unimaginable just decades ago. A single night of intensive Planet 9 hunting can produce over 1 terabyte of information, which represents enough digital data to completely fill hundreds of traditional DVDs. Massive supercomputers work continuously around the clock to process these enormous image collections, applying incredibly sophisticated algorithms to digitally subtract all known stars and galaxies, leaving behind only the moving objects that might potentially be planets. The search strategies employed by different teams have evolved into a genuine art form that balances scientific precision with educated guesswork. Some research teams focus their telescope time on specific areas of sky where Planet 9 should theoretically appear brightest, assuming it's positioned closer to the Sun during its current orbital phase. Other teams deliberately search what astronomers call the opposition point, which represents the direction in space directly opposite our Sun, where Planet 9 would display the most apparent motion against the background star field. Each telescope facility brings completely unique advantages to this cosmic treasure hunt. The Large Synoptic Survey Telescope, currently under construction in the high-altitude deserts of Chile, will absolutely revolutionize the search when it becomes fully operational. This revolutionary facility will systematically photograph the entire visible sky every few nights, creating an unprecedented movie of the cosmos that should reveal any moving objects larger than just a few hundred miles across. But despite years of incredibly intensive searching involving thousands of hours of precious telescope time, Planet 9 continues to masterfully elude detection. Every single promising signal has ultimately turned out to be a false alarm. Every candidate object has eventually proven to be something completely different from what researchers hoped to find. The electronic hunters scanning the skies were about to learn a harsh lesson about cosmic deception. Space is absolutely full of cosmic mimics and false prophets that love to fool even the most experienced astronomers. The universe seems to take perverse pleasure in playing elaborate tricks on astronomers, hunting for Planet 9. Every year brings dozens of genuinely promising candidates, representing faint, slowly moving objects detected at the absolute edge of telescope sensitivity limits. Each discovery triggers weeks of intense excitement, immediate follow-up observations, and complex orbital calculations, only to end in the crushing disappointment of yet another devastating false alarm. The hunt for Planet 9 has inadvertently become a masterclass in cosmic deception and the countless ways the universe can fool human observers. The most common imposters masquerading as Planet 9 are distant asteroids, pretending to be planets through optical illusion. These chunks of rock and ice normally orbit in the asteroid belt located between Mars and Jupiter, but when they reach the far side of their elliptical orbits, they appear to move slowly against background stars, creating motion patterns exactly like Planet 9 would display. Only careful observations extended over several months can reveal their true nature and crushing identity. Think of this phenomenon like mistaking a distant airplane for a slow-moving satellite in the night sky. From far away, a fast-moving object can appear to crawl across the heavens, creating the perfect illusion of something much more distant and exotic. Asteroids positioned at opposition, when Earth lies directly between them and our Sun, create exactly this kind of maddening optical illusion that has fooled countless research teams. Computer glitches add another incredibly frustrating layer to the search process. High-energy cosmic rays, striking sensitive telescope detectors create bright spots that appear completely indistinguishable from real stars or planets in individual images. Software algorithms specifically designed to identify moving objects, sometimes incorrectly, flag these random detector hits as potential Planet 9 candidates, sending dedicated astronomers on expensive wild goose chases that lead absolutely nowhere. Hot pixels on camera sensors cause similar maddening problems for search teams. These represent individual detector elements that malfunction and record bright signals even when no actual light hits them. Hot pixels appear in identical locations in every image captured, but when telescopes move between exposures, these faulty pixels can create the convincing illusion of an object that appears to jump mysteriously from place to place across the sky. One of the most heartbreaking false alarms occurred in 2018, when a respected team announced the discovery of an object they dramatically named Far Far Out, potentially representing the most distant object ever found in our solar system. Initial observations suggested it was positioned 3 times farther from our Sun than Pluto, placing it squarely within Planet 9's predicted territory. Months of intensive follow-up observations revealed the absolutely devastating truth. Far Far Out was indeed extremely distant, but it was simply another Kuiper Belt object, larger than initially expected but nowhere near massive enough to be the elusive Planet 9. The discovery provided scientifically valuable data, but proved emotionally crushing for researchers who had genuinely hoped they'd found the holy grail of planetary science. Atmospheric distortions create their own unique brand of false hope for search teams. When starlight travels through Earth's atmosphere, it gets bent and distorted by pockets of air at different temperatures. This causes stars to appear to jump around slightly from image to image, creating completely artificial motion that can fool even sophisticated computer algorithms into flagging them as moving objects. The psychological toll of repeated false alarms weighs incredibly heavily on dedicated Planet 9 hunters. Each promising candidate requires intense focus and genuine hope, followed by the methodical process of determining its disappointing true nature. This repeated cycle of excitement and crushing disappointment has become a genuine occupational hazard for astronomers involved in the search. Some false alarms result from simple human error compounded by exhaustion. Tired researchers working through long nights sometimes misread coordinates, transpose critical numbers, or make calculation mistakes that transform ordinary asteroids into apparent Planet 9 candidates. The enormous pressure to make the discovery of the century can cloud scientific judgment and lead to dangerous wishful thinking. Despite years of false alarms and scientific dead ends, the search continues with completely undiminished intensity and determination. But the cosmic game of hide and seek was teaching astronomers something absolutely crucial about detection strategies. They needed to completely abandon the obvious places and think like forensic investigators. Sometimes the most effective way to find something completely invisible is to carefully study the shadows it casts across the cosmic landscape. While powerful telescopes continue scanning the skies for direct glimpses of Planet 9, a completely different breed of detective work is systematically uncovering its gravitational fingerprints throughout every corner of our solar system. These cosmic forensics experts read gravitational scars exactly like experienced detectives, examining a complex crime scene, finding undeniable evidence of Planet 9's influence in places absolutely no one thought to look before. The first major clue emerges from the Kuiper Belt's mysteriously sharp outer edge, a phenomenon that has puzzled astronomers for decades. Beyond approximately 50 times Earth's distance from our Sun, the population of small icy objects drops off dramatically and inexplicably, as if something incredibly powerful swept them away with tremendous force. Computer simulations demonstrate that Planet 9's immense gravity could have functioned like a cosmic vacuum cleaner operating over millions of years, either violently ejecting objects entirely from our solar system or methodically shepherding them into the same tilted orbital patterns we observe throughout the outer regions today. Think of this phenomenon like walking through a dense forest and suddenly discovering a perfectly circular clearing where absolutely no trees grow. You don't need to actually see what created that clearing to know with absolute certainty that something extraordinarily powerful was operating there. Planet 9's gravitational influence has carved similar clearings throughout the outer solar system, invisible to casual observation but completely obvious to experienced researchers who understand what to look for. The strange and unpredictable behavior of periodic comets provides another crucial piece of this cosmic puzzle. These frozen snowballs follow generally predictable paths that return them to the inner solar system every few decades or centuries with clockwork precision. But certain comets display subtle changes in their orbital characteristics that simply cannot be explained by gravitational interactions with any known planets in our solar system. Comet Mashol's follows a particularly suspicious and telling path through space. Its orbit tilts by approximately 60 degrees relative to the main orbital plane of our solar system, and it approaches our Sun from a direction that aligns suspiciously well with Planet 9's predicted current location. The mathematical odds of this representing mere coincidence are vanishingly small, approaching statistical impossibility. Even more intriguing is the peculiar population of objects called centaurs, small cosmic bodies that orbit in the chaotic region between Jupiter and Neptune. These cosmic wanderers should theoretically be randomly distributed throughout their region according to basic gravitational mechanics. Instead, they show a subtle but unmistakable bias towards specific orbital orientations that seem to follow a hidden pattern. Advanced computer models reveal that Planet 9's persistent gravity could have gradually nudged these objects into their current suspicious configuration over millions of years through patient gravitational shepherding that operates like invisible hands arranging cosmic furniture. The evidence extends dramatically all the way inward to our familiar inner solar system, affecting planets we see every night. The orbits of known planets show tiny but persistent discrepancies that have genuinely puzzled astronomers for decades without satisfactory explanation. Mars arrives at certain predicted points in its orbit, approximately a few seconds earlier than our most sophisticated calculations predict. Jupiter's measured position differs from theoretical calculations by tiny but consistently measurable amounts that accumulate over time. These discrepancies seem so incredibly small that scientists initially attributed them to measurement errors or incomplete knowledge about asteroid masses affecting our calculations. But something remarkable happens when astronomers add Planet 9's predicted mass and location to their computational models. Many of these mysterious tiny errors simply disappear, as if the calculations suddenly make perfect sense. It's exactly as if Planet 9 has been gently tugging on all the other planets with invisible gravitational strings for billions of years, creating subtle but detectable influences throughout our entire solar system. The precise timing of these gravitational effects provides absolutely crucial information about Planet 9's current location in space. Gravitational influences travel at exactly the speed of light, creating a cosmic communication network. So Planet 9's effect on inner planets depends not just on its mass and distance, but on where it's positioned right now during its enormously long orbital journey. By carefully studying these timing discrepancies with incredible precision, astronomers can narrow down where Planet 9 should appear in the sky at this exact moment. It's like triangulating the position of a hidden radio transmitter by measuring the precise time it takes signals to reach different receivers positioned around the globe. Recent studies of spacecraft trajectories have revealed additional mysterious anomalies that strengthen the case for Planet 9's existence. The Cassini probe, which spent 13 years orbiting Saturn and collecting invaluable data, experienced tiny but persistent deviations from its predicted flight path that couldn't be explained by known gravitational influences. Similar effects have been detected in the trajectories of both Voyager probes as they journey toward interstellar space, carrying humanity's messages to the cosmos. These spacecraft anomalies are incredibly small, measured in mere millimeters per second, but they remain perfectly consistent with gravitational perturbations from a massive hidden object operating in the outer solar system. Each additional piece of evidence systematically builds an increasingly compelling case that Planet 9 isn't just passively hiding somewhere beyond Neptune's orbit. It's actively shaping the gravitational dynamics of our entire cosmic neighborhood, like a hidden conductor, directing a vast astronomical orchestra. The indirect evidence has become so overwhelmingly compelling that some astronomers now argue we've already discovered Planet 9 through its unmistakable gravitational effects, even though absolutely no one has managed to see it directly through any telescope. But understanding how such a massive world could possibly form so incredibly far from our Sun remains one of the greatest unsolved puzzles in modern planetary science. Building a world like Planet 9 in the outer solar system resembles trying to construct a massive skyscraper using building materials scattered randomly across an entire continent. The traditional theory of planetary formation works absolutely beautifully for explaining our inner solar system, where Earth, Mars, Venus, and Mercury assembled from countless violent collisions of rocky debris over millions of years. But this same theory breaks down completely when applied to Planet 9's distant realm, where the raw materials needed for planet building are spread impossibly thin across distances that dwarf human comprehension. Picture the early solar system as a giant construction site spanning billions of miles. Close to our Sun, the site bustled with constant activity as millions of rocky chunks collided and stuck together like cosmic Lego blocks, gradually building the terrestrial planets we know today. But move outward beyond Neptune's current orbit, and that same construction site transforms into a vast, nearly empty wasteland, where building materials are separated by distances measured in millions of miles, making planetary construction seem virtually impossible. The fundamental problem plaguing Planet 9's formation lies in material density. In the region where Planet 9 orbits today, there simply wasn't enough solid material available to build a world 10 times Earth's mass using conventional planetary formation processes. The solar nebula, representing the disk of gas and dust from which all planets formed, contained mostly hydrogen and helium at those extreme distances, with only trace amounts of heavier elements needed to build rocky planetary cores. At Planet 9's incredible distance from our Sun, this already challenging process would take approximately 100 times longer than normal planetary formation. Think of this situation like trying to build a house during a brief 10-minute rainstorm, except your construction site is so impossibly remote that it takes an entire hour just to carry each individual piece of lumber to the foundation. By the time you've finally gathered enough materials to start meaningful construction, the storm has completely passed and you're left holding an incomplete structure that can never be finished. The raw materials you desperately need have simply vanished into the cosmic void. The core accretion model, which represents the standard scientific explanation for how all giant planets form throughout the universe, requires a solid planetary core of at least 10 Earth masses before any world can begin successfully capturing significant amounts of gas from the surrounding solar nebula. But building such a massive core at Planet 9's predicted distance would require hundreds of millions of years of patient material accumulation, occurring long after all the available gas has permanently dissipated into space. This creates an impossible timeline that defies the known laws of planetary formation. Some innovative astronomers have proposed fascinating alternative formation mechanisms that could theoretically work in the sparse environment of the outer solar system. The gravitational instability model suggests that massive planets can form directly from the sudden collapse of unusually dense regions in the gas disk, without needing to slowly build up solid cores first through collision-based processes. This revolutionary process works dramatically faster than traditional formation methods, taking only thousands of years instead of millions, but it requires very specific environmental conditions that may not have existed anywhere in our early solar system. The streaming instability offers another intriguing possibility for solving Planet 9's formation mystery. This sophisticated mechanism concentrates solid particles into incredibly dense clumps through complex interactions with the surrounding gas disk. Under exactly the right conditions, these concentrated clumps can collapse directly into planetary cores, completely bypassing the slow collision-based accumulation process entirely. But even these promising alternative mechanisms struggle desperately to explain how Planet 9 could have possibly formed at its current location. The outer regions of the primordial solar nebula were simply too sparse and too incredibly cold to support rapid planet formation through any known physical process that scientists currently understand. Recent studies of exoplanets orbiting distant stars have revealed something absolutely shocking. Mini-Neptunes like Planet 9 are incredibly common throughout the galaxy, often orbiting much closer to their host stars than Planet 9 orbits our Sun. This fascinating observation has led to a completely revolutionary new theory about Planet 9's mysterious origin, one that doesn't require it to form where it currently resides in the outer darkness. What if Planet 9 actually formed much closer to our Sun, in regions where conditions were ideal for rapid planet growth, and then migrated outward to its present location through violent gravitational interactions with other planets over millions of years? This migration scenario opens up entirely new possibilities for understanding how our solar system's most mysterious world came to exist in its current impossible location. Planet 9 might actually be a cosmic exile, banished from the inner solar system by gravitational warfare that reshaped our entire cosmic neighborhood. The migration theory paints a dramatically different and far more violent picture of our solar system's early history, one filled with planetary violence, gravitational battles, and cosmic refugees desperately fleeing their original homes. Instead of forming peacefully at its current location, Planet 9 might have been born much closer to our Sun, only to be violently ejected to the outer darkness through a series of gravitational encounters that completely reshaped the entire solar system. Picture the early solar system as a cosmic pool table with massive planets acting as cue balls striking each other in a chaotic game that lasted millions of years. In this incredibly violent environment, gravitational interactions could fling entire planets across enormous distances, turning orderly orbital arrangements into complete cosmic chaos. This incredible story begins approximately 4.5 billion years ago, when our solar system was still young, unsettled, and incredibly dangerous. Sophisticated computer simulations suggest that the region between Jupiter and Neptune, originally contained not 4 giant planets as we see today, but actually 5 massive worlds. The extra world, quite possibly Planet 9 itself, originally orbited somewhere between Saturn and Uranus in a gravitational configuration that was fundamentally unstable and doomed to collapse. Think of this situation like 5 people desperately trying to sit comfortably on a 4-person bench. Someone absolutely has to give way, and in the early solar system, that unlucky someone was likely the smallest of the giant planets. Through a series of increasingly close gravitational encounters with Jupiter and Saturn, this 5th planet found itself trapped in an increasingly eccentric orbit that eventually carried it far beyond Neptune's protective domain. The ejection process wasn't sudden or violently explosive. Instead, it unfolded gradually over millions of years, through a mechanism astronomers call the 9's model, named after the French city where it was originally developed. This model describes exactly how gravitational interactions between the giant planets could have dramatically rearranged the entire outer solar system through patient cosmic choreography. Jupiter, the undisputed heavyweight champion of our solar system, played the role of cosmic bully in this scenario. Its immense gravitational influence acted like a massive gravitational slingshot, accelerating smaller planets to higher speeds with each dangerous encounter. Over extended time periods, these repeated gravitational kicks could boost a planet's velocity enough to send it careening helplessly toward the outer solar system. But permanent exile wasn't inevitable for every displaced world. Computer simulations demonstrate that roughly half of all ejected planets don't escape their solar systems entirely. Instead, they end up trapped in distant, highly elliptical orbits, exactly the kind of elongated orbital path predicted for Planet 9. These cosmic refugees retain enough gravitational connection to their birth star to remain permanently bound, but they're banished to the cold outer reaches, where they can no longer interfere with the remaining planet's stable orbits. The migration theory elegantly solves the formation problem that has plagued astronomers for decades. If Planet 9 formed closer to our Sun, perhaps at Jupiter's current distance, it would have had access to abundant building materials and could have grown to its predicted massive size within the crucial 10 million year window before the solar nebula permanently disappeared. This theory also explains several puzzling features of our solar system's architecture that have confused scientists for generations. The late heavy bombardment, a violent period occurring about 4 billion years ago when asteroids and comets rained down catastrophically on the inner planets, could have been directly triggered by Planet 9's dramatic ejection. As the migrating planet passed through the asteroid belt and Kuiper belt during its outward journey, it would have scattered countless small objects into chaotic orbits that eventually collided with Earth, Mars, and other inner planets, creating the cratered surfaces we observe today. The migration theory makes specific predictions about Planet 9's composition and internal structure that could be tested once this elusive world is finally discovered. A world that formed closer to the Sun would have a completely different mixture of rock, ice, and gas than one that formed in the outer solar system. But the migration theory faces one significant challenge that threatens its validity: timing. Confirming the discovery of Planet 9 requires patience that spans entire human lifetimes, creating challenges that make the initial search seem simple by comparison. Even if a powerful telescope manages to capture the very first photons of light reflected from Planet 9 tomorrow morning, proving that the discovery represents genuine reality would require years of painstakingly precise observations that push our current technology to its absolute breaking points. The observational challenges facing dedicated Planet 9 hunters make actually finding this mysterious world seem remarkably easy compared to definitively confirming it truly exists, where we think it does. The fundamental problem plaguing confirmation efforts lies in motion, or more accurately, the almost complete lack of detectable movement. Planet 9 moves so incredibly slowly across our night sky that detecting its motion requires observations carefully separated by months or even entire years of patient waiting. At its predicted distance from our Sun, this hidden giant would require between 10,000 and 20,000 years to complete just a single orbital journey around our solar system. That means Planet 9 moves less than 2 arc minutes per year across the cosmic backdrop, representing approximately 1/15 the width of the full moon as seen from Earth. Think of this challenge like trying to prove that the hour hand on a wall clock is actually moving by taking photographs just a few minutes apart. The motion is absolutely real and continuous, but it's far too slow to detect without extremely precise measurements conducted over extended periods. Planet 9's motion against the background field of distant stars would be barely perceptible, even to our most sensitive and sophisticated telescopes operating at peak performance. The brightness challenge adds another incredibly complex layer to the confirmation process. Planet 9 would appear as nothing more than a faint star-like point of light, completely indistinguishable from billions of actual stars and distant galaxies scattered across the cosmic canvas. Only by systematically observing the exact same patch of sky repeatedly over months, and carefully looking for objects that move between sequential exposures, can astronomers hope to separate genuine planets from the overwhelming cosmic background noise. But even successfully detecting motion isn't nearly enough to confirm a legitimate Planet 9 discovery. Asteroids, comets, and countless other solar system objects also move against background stars, often at rates remarkably similar to what Planet 9 would display. Distinguishing between a genuinely distant planet and a much closer asteroid requires incredibly precise measurements of the object's brightness variations, color characteristics, and complex orbital mechanics. The orbital calculation process proves particularly demanding and mathematically intensive, confirming that any discovered object follows the predicted Planet 9 orbit theoretically requires tracking its position for at least one complete orbital cycle, which could take 20,000 years to observe fully. Obviously, astronomers cannot wait that impossibly long for scientific confirmation. Instead, they must observe the object continuously for several years and use the relatively small arc of its observed orbit to extrapolate the complete orbital path through sophisticated mathematical modeling. This extrapolation process resembles trying to determine the exact shape of a giant circle by examining only a tiny curved segment under a microscope. Small measurement errors or instrument calibration problems can lead to dramatically different orbital predictions, making it dangerously easy to mistake a small nearby asteroid for a distant planet, or vice versa. Weather conditions and atmospheric turbulence add completely unpredictable variables to the already challenging confirmation process. Planet 9 observations require the darkest possible skies with absolutely no moon visible and minimal atmospheric disturbance that could distort measurements. Such ideal conditions occur only during a few precious nights per month at the world's best observatory sites, and even then, unexpected clouds or high winds can completely shut down critical observations. The extreme faintness of Planet 9 means that each individual observation requires many hours of continuous exposure time to collect enough photons for precise scientific measurements. During these marathon exposures, Earth's constant rotation causes background stars to drift slowly across the telescope's field of view, requiring incredibly sophisticated tracking systems to keep the telescope pointed precisely at the target location. Cosmic ray strikes on sensitive telescope detectors create additional frustrating complications for Planet 9 hunters. These high-energy particles arriving from deep space randomly impact the electronic sensors, creating bright spots that can perfectly mimic the appearance of genuine faint astronomical objects. Distinguishing real planets from cosmic ray artifacts requires taking multiple images and comparing them with extreme care. The psychological challenges facing Planet 9 hunters may prove as demanding as the technical obstacles they encounter. Years of disappointing false alarms and crushing results have created a scientific environment where extraordinary claims absolutely require extraordinary evidence to be accepted. Any announced Planet 9 discovery will face intense scrutiny from skeptical colleagues who demand multiple independent confirmations from different research teams using completely different instruments and methods. The fierce competition between rival research teams adds tremendous pressure to announce discoveries quickly and claim priority, but premature announcements can permanently damage scientific reputations if the claims don't hold up under rigorous peer review and independent verification. The delicate balance between being first to announce a world-changing discovery and being absolutely certain the discovery represents reality creates enormous psychological stress for astronomers involved in the search. Despite these overwhelming challenges, the search continues with completely unprecedented intensity, driven by the knowledge that finding Planet 9 would represent one of the greatest discoveries in the entire history of astronomy, ranking alongside the discoveries of Neptune and Pluto. But these dedicated researchers aren't searching alone in isolation. Teams around the world are joining this cosmic hunt with increasingly sophisticated strategies and cutting-edge technology. The hunt for Planet 9 has evolved into the most competitive treasure hunt in modern astronomy. Around the globe, rival teams of brilliant astronomers are racing against each other and against time itself, each hoping to claim the discovery that will secure their permanent place in history, alongside legendary figures like Galileo and Kepler. This isn't simply scientific collaboration anymore. This represents a high-stakes competition where the winner claims everything and the losers become forgotten footnotes in future astronomy textbooks. The Subaru telescope team stationed in Hawaii leads one of the most systematic and methodical searches ever attempted. Using their revolutionary wide-field camera to systematically scan the northern sky in a precise grid pattern that ensures absolutely no potential hiding spot goes unexplored. Led by accomplished astronomer Scott Shepard, this dedicated team has already discovered dozens of new objects lurking in the outer solar system, with each discovery providing additional crucial clues about Planet 9's gravitational influence throughout our cosmic neighborhood. Their strategy focuses specifically on the opposition region, representing the portion of sky positioned directly opposite our Sun, where Planet 9 would appear brightest and display the most detectable motion against background stars. Night after night, they return to identical patches of sky with monastic dedication, searching for absolutely anything that moves between sequential exposures. It's methodical, patient work that requires the unwavering discipline of monks combined with the precision of skilled surgeons. Meanwhile, the Dark Energy Survey team pursues a completely different approach, systematically mining their enormous database of southern sky images for objects that previous searchers somehow missed. Their survey wasn't originally designed to find planets, but it covers such a vast area and reaches such incredibly faint magnitudes that it might accidentally capture Planet 9 in its digital net. Japan's groundbreaking leadership in wide-field astronomy through the revolutionary Subaru telescope represents a massive national investment in astronomical discovery that spans decades of commitment. American research teams, supported by enormous funding from NASA and the National Science Foundation, bring completely different technological advantages to this cosmic hunt. European astronomers contribute their own sophisticated search strategies through world-class facilities, like the Very Large Telescope stationed in Chile's Atacama Desert. Each competing team guards their search strategies and preliminary results with the kind of secrecy typically reserved for top-secret military operations. Astronomical conferences have transformed into diplomatic battlegrounds, where research teams share just enough information to maintain scientific credibility while carefully holding back the crucial details that might give their competitors a decisive advantage. The stakes surrounding this discovery couldn't possibly be higher for anyone involved. The team that successfully finds Planet 9 will secure serious Nobel Prize consideration, permanent fame throughout the astronomy community, and guaranteed funding for future research projects that will sustain their entire careers. The discovery will be officially named after the lead investigator, ensuring scientific immortality in exactly the same way that Uranus honors William Herschel and Neptune honors John Couch Adams. But this intense competition has also driven remarkable innovation in search techniques and data analysis methods that benefit everyone. Competing teams push their expensive instruments to detection limits that were completely unimaginable just a decade ago. They've developed revolutionary new algorithms for identifying moving objects, created innovative strategies for eliminating false positives, and discovered new ways to squeeze maximum information from every precious photon of light their telescopes manage to collect. The rivalry has created beneficial redundancy that serves science as a whole. Multiple independent searches dramatically increase the chances that Planet 9 will eventually be found, and they provide crucial cross-checks that reduce the likelihood of false discoveries making it into the scientific literature where they could mislead future research. As the search intensifies and technology continues improving at breakneck speed, the discovery of Planet 9 feels increasingly inevitable. The question plaguing astronomers is no longer if this mysterious world will be found, but precisely when and by which team. Inside powerful supercomputers worth millions of dollars, digital versions of our entire solar system are systematically revealing Planet 9's deepest secrets. While telescopes scan the real sky for glimpses of our mysterious ninth planet, computer scientists are building incredibly detailed virtual solar systems where they can fast forward through billions of years of planetary evolution in just a matter of hours. These digital universes have become the secret weapon in the hunt for Planet 9, predicting exactly where it should be hiding and precisely how it arrived at its current location. The most sophisticated simulations begin with our solar system, as it existed 4.5 billion years ago, representing a chaotic disk of gas, dust, and countless planetary embryos orbiting a young, violent sun. The supercomputers then calculate how gravity pulls on every single object, tracking millions of complex interactions as the system slowly evolves into its current familiar configuration. Think of this process like playing the ultimate video game, where every particle follows the laws of physics with perfect precision. The game runs at incredible superspeed, with each second of computer time representing millions of years of actual cosmic history. Scientists can pause the simulation at any point, rewind it like a movie, or change the starting conditions to see how different scenarios play out across geological time. These virtual experiments have revealed absolutely stunning insights about Planet 9's crucial role in shaping our entire solar system. In simulations that include a massive ninth planet, the outer solar system evolves into something that looks remarkably similar to what we observe today in reality. Remove Planet 9 from the simulation entirely, and the virtual solar system becomes completely chaotic, with objects scattered randomly, instead of clustering in the precise patterns we see in our actual cosmic neighborhood. The simulations work by solving what mathematicians call the n-body problem, calculating how multiple massive objects influence each other through gravitational forces over extended periods. For Planet 9 simulations, that means tracking the incredibly complex gravitational interactions between our Sun, 8 known planets, thousands of asteroids and comets, and the hypothetical ninth planet itself. Modern supercomputers can handle these mind-boggling calculations, but just barely. A single comprehensive simulation tracking the evolution of our entire solar system over 4 billion years requires weeks of continuous computation time on machines that cost millions of dollars to build and operate. The calculations are so computationally intensive that research teams must compete fiercely for time on national supercomputer facilities, submitting detailed proposals that are evaluated like requests for precious telescope time at major observatories. The simulations have predicted several key features of Planet 9 that directly guide observational searches conducted by teams around the world. They suggest this mysterious planet should have a mass between 5 and 20 times Earth's mass, orbit between 400 and 800 times farther from the Sun than Earth, and follow a highly elliptical path that takes 15,000 to 25,000 years to complete. But the simulations also reveal a frustrating and disappointing truth. Planet 9 could be hiding almost anywhere within an enormous search zone that covers thousands of square degrees of sky. Its orbit is so incredibly elongated that it spends most of its time at vast distances where it appears incredibly faint to even our most powerful telescopes. The simulations clearly show that Planet 9 is most likely to be near aphelion, representing the farthest point in its orbit, where it would be almost impossible to detect with current technological capabilities. Recent simulations have explored increasingly exotic scenarios that push the boundaries of planetary science. What if Planet 9 isn't traveling alone, but represents part of a binary system with another massive object? What if it has a large moon that significantly affects its motion through space? What if it's actually two smaller planets orbiting close together in a complex gravitational dance? Each possibility dramatically changes the predictions and opens completely new search strategies for astronomers to explore. The most intriguing simulations explore Planet 9's mysterious past. Computer models suggest that if Planet 9 formed closer to the Sun and migrated outward through gravitational interactions, it should have left a clear trail of evidence in the form of displaced asteroids and comets. These gravitational scars should still be visible today, providing a detailed roadmap to Planet 9's migration history. The simulations have also predicted the discovery of additional objects that should cluster under Planet 9's gravitational influence. Several of these predicted objects have actually been found by observational surveys, providing powerful confirmation that the computer models are on the right track. As computing power increases exponentially and algorithms improve, the simulations are becoming precise enough to predict not just where Planet 9 should be, but when it will be easiest to find during its enormously long orbit. But even the most sophisticated computer model can't overcome the fundamental challenge of detecting something so distant and dark. Planet 9 dances to gravitational music that takes 20,000 years to complete a single song. Understanding Planet 9's orbit requires thinking in timescales that completely dwarf human civilization. While Earth completes its familiar yearly journey around the Sun, Planet 9 crawls through space so slowly that it has barely moved since the pyramids were built. This incredible discovery continues to challenge everything we thought we knew about our cosmic neighborhood. Planet 9's orbital mechanics operate on a scale so vast and complex that they completely transform our fundamental understanding of what it truly means to be a planet in our solar system. The mathematics describing Planet 9's orbit read like epic poetry written in the elegant language of physics, telling a story that spans geological time periods. Its path around our Sun stretches into an absolutely enormous ellipse that defies human comprehension. This isn't the nearly circular orbit that Earth follows like a well-behaved cosmic citizen. Instead, Planet 9 traces a cosmic egg shape that carries it from relatively close to our Sun all the way out to the very edge of interstellar space, where our solar system begins to fade into the cosmic void. At perihelion, representing its closest approach to our Sun, Planet 9 still orbits farther out than Neptune, maintaining its status as the most distant major planet in our solar system. But at aphelion, its farthest point from the Sun, it ventures outward to nearly 1,000 times Earth's distance from our solar center. At that incredibly remote location, our Sun appears as nothing more than just another bright star scattered across the cosmic canvas, providing less actual warmth than a candle flame viewed from across an entire football field. The temperature at Planet 9's surface would plunge to unimaginable depths, creating conditions more hostile than anything humans have ever encountered. Think of Planet 9's orbit like a cosmic roller coaster that takes 20 millennia to complete just a single ride through space. For the vast majority of that incredible journey, Planet 9 cruises through the outer reaches of our solar system, where it moves at barely walking speed relative to the background field of distant stars. Only during its brief passage through the inner portions of its elliptical orbit does Planet 9 accelerate to the relatively breakneck pace of a few miles per second, still incredibly slow by cosmic standards, but fast enough to be potentially detectable by our instruments. The orbital mechanics perfectly explain why Planet 9 has remained completely hidden from human observation for so long. It spends roughly 90% of its orbital period lurking in the outer reaches of its elliptical path, where it appears incredibly faint and moves almost imperceptibly against the stellar background that fills our night sky. Current telescope surveys are most likely to successfully spot Planet 9 only during the brief periods when it ventures into the relatively inner parts of its orbit, becoming bright enough and fast enough to distinguish from background objects. But here's the cruel irony that keeps astronomers awake at night. Planet 9's orbital mechanics suggest it might currently be positioned near aphelion at its farthest and faintest point from our Sun. If this prediction proves true, it could remain essentially undetectable for centuries or even millennia, slowly brightening as it begins the 10,000-year journey back toward perihelion. The gravitational choreography becomes even more incredibly complex when you consider Planet 9's interactions with all the other planets in our solar system. Its immense orbit carries it through gravitational territories controlled by different planets at different times during its marathon journey. Sometimes Planet 9 feels the distant but persistent tug of Jupiter's massive gravity. Other times it responds to Neptune's gravitational influence. These competing gravitational forces create subtle perturbations in its orbit that could potentially provide crucial clues to its current location if we can detect and measure them accurately. The orbital inclination adds another fascinating layer of complexity to this cosmic puzzle. Planet 9's orbit is tilted approximately 15 to 25 degrees relative to the plane where all the other planets orbit in orderly formation. This means it spends part of its time above the plane of the solar system and part of its time below, like a cosmic Ferris wheel tilted at a dramatic angle. This tilted orbit has profound implications for search strategies employed by astronomers worldwide. Planet 9 could currently be located far above or below the plane where most astronomical surveys focus their precious telescope time and attention. Telescopes optimized for finding objects in the plane of the solar system might be looking in entirely the wrong direction. The orbital mechanics also significantly influence Planet 9's rotation period, an internal structure in ways we're only beginning to understand. Planet 9 might be playing the ultimate game of cosmic hide-and-seek by hiding in the wrong century entirely. The cruel mathematics of orbital timing could explain why the most intensive planet hunt in astronomical history has come up completely empty-handed, despite years of dedicated searching. Planet 9's enormously long orbit means that its brightness and visibility change dramatically over time. Scales measured in thousands of years, we might simply be living in the wrong historical era to spot our solar system's most elusive member. Consider the timeline problem from Planet 9's perspective across deep time. If it completes one complete orbit every 20,000 years, then the entire span of human civilization has existed for less than half of one single orbital period. The complete history of astronomy from Galileo's first telescope to today's sophisticated digital sky surveys represents just 2% of Planet 9's cosmic year. During most of its orbital journey, Planet 9 lurks in the outer darkness where it reflects barely enough sunlight to register on even our most sensitive telescopes. But for perhaps 1,000 or 2,000 years out of every 20,000, it ventures close enough to become detectable with technology like ours. Think of this phenomenon like a lighthouse with an incredibly long rotation period spanning millennia. For most of the time, its beam points away from you into empty space. Only occasionally does the beam sweep across your location, briefly illuminating everything before disappearing again for decades or centuries. The observational window for Planet 9 detection might be as narrow as just a few centuries out of every 20 millennia. If Planet 9 reached its closest approach to our Sun during the time of ancient Rome, it would have appeared as a faint star-like object visible to telescopes that wouldn't be invented for another 1,500 years. By the time astronomers finally developed the sophisticated tools necessary to find it, Planet 9 would have already begun its journey back to the outer darkness, becoming progressively fainter with each passing century. Alternatively, Planet 9 might currently be approaching its closest point to our Sun, gradually brightening over the coming centuries until it becomes easily detectable. In this scenario, future astronomers might genuinely wonder how 21st century scientists could have possibly missed something so obvious. The timing problem extends far beyond simple brightness considerations. Planet 9's motion against background stars also varies dramatically depending on where it currently resides in its orbit. Near perihelion, it would appear to move relatively quickly, making it much easier to distinguish from static background stars and distant galaxies. Near aphelion, its motion becomes so incredibly slow that it could take years of careful observation to confirm that it's actually moving at all relative to the cosmic background. Current estimates suggest Planet 9 might be anywhere from 400 to 800 times farther from the Sun than Earth. That enormous uncertainty translates into vastly different predictions for its brightness and detectability. At 400 times Earth's distance, Planet 9 might be just barely detectable with our current telescope technology. At 800 times Earth's distance, it could remain completely invisible for decades to come. The timing problem creates a maddening paradox for dedicated Planet 9 hunters that could define the next generation of astronomical research. Recent studies have desperately attempted to constrain Planet 9's orbital phase by carefully analyzing the clustering patterns of distant objects under its gravitational influence. Some sophisticated models suggest Planet 9 is currently positioned near aphelion, its farthest point from the Sun, which would perfectly explain why it has completely eluded detection despite the most intensive astronomical searches in human history. But even if Planet 9 is currently too faint to see with our existing technology, Dedicated astronomers are developing revolutionary new strategies that don't require direct detection at all. Finding Planet 9 requires pushing the absolute limits of what darkness means in the cosmos. The brutal mathematics of brightness and distance conspire to make Planet 9 one of the faintest objects astronomers have ever attempted to detect. Understanding just how impossibly dim this mysterious world appears requires thinking about light in ways that challenge human intuition and push telescope technology to its absolute breaking point. Brightness in astronomy follows an absolutely unforgiving law called the inverse square rule that shows no mercy to distant objects. Double the distance to any object, and it appears 4 times fainter. Triple the distance, and it becomes 9 times dimmer. Planet 9 orbits so incredibly far from our Sun that this mathematical cruelty transforms a world potentially the size of Neptune into something barely brighter than a flickering candle viewed from 3,000 miles away. The crushing calculations start with sunlight itself, the source of all reflected light we might detect from Planet 9. At Earth's comfortable distance from the Sun, our star delivers approximately 1,300 watts of energy per square meter, enough raw power to operate a hairdryer. But at Planet 9's predicted location in the outer darkness, that same sunlight is spread out over such an enormous area that each square meter receives less than 1 measly watt of energy. It's like desperately trying to heat an entire house using nothing but a single birthday candle. Planet 9 doesn't generate any light of its own like a star. It merely reflects the feeble sunlight that reaches its frozen surface after traveling hundreds of billions of miles through empty space. The amount of light it manages to reflect depends critically on its albedo, representing the fraction of incoming sunlight that bounces back toward Earth instead of being absorbed by its surface materials or atmospheric envelope. Think of albedo like the fundamental difference between a mirror and a piece of charcoal. Fresh snow reflects about 90% of the light that strikes it, creating brilliant white landscapes. Charcoal, by contrast, reflects less than 5% of incoming light, appearing dark and absorbing most illumination. Most objects discovered in the outer solar system are unfortunately dark, much closer to charcoal than snow in their reflective properties. This makes them even harder to see than their enormous distances would suggest through pure mathematics alone. If Planet 9 possesses an albedo similar to Neptune, reflecting about 40% of incoming light, it would appear as a 25th magnitude object even in our most powerful telescopes. That represents approximately 10 million times fainter than the faintest stars visible to the naked eye on the darkest nights. If its surface proves darker, like most objects lurking in the Kuiper belt, it could register as 26th or even 27th magnitude, so incredibly faint that detecting it would push current telescope technology far beyond its original design limits. The brightness calculations become even more pessimistic when you consider atmospheric absorption effects that steal precious photons. Earth's atmosphere constantly absorbs and scatters light, making faint objects appear even dimmer than they actually are. On the best nights at the highest mountaintop observatories, atmospheric effects still steal about 20% of the light from distant objects. But determined astronomers have found ingenious ways to fight back against the cosmic darkness. Modern telescope detectors are so extraordinarily sensitive they can register individual photons of light striking their surfaces. Advanced image processing techniques can enhance faint signals by combining multiple exposures and filtering out electronic noise. Adaptive optics systems use flexible mirrors to counteract atmospheric turbulence in real time, producing images nearly as sharp as those from space telescopes. The search for Planet 9 has driven the development of revolutionary new brightness measurement techniques that squeeze every possible photon from the darkness. Some teams use sophisticated infrared detectors that might catch the faint heat signature Planet 9 radiates into space from its internal energy. Others are preparing for the next generation of ground-based telescopes that will have mirrors 4 times larger than anything currently available. Meanwhile, new discoveries are either confirming Planet 9's existence or challenging everything we thought we knew about the outer solar system. Every few months, astronomers announce the discovery of another distant object lurking in the outer solar system's frozen wilderness. Each new find becomes a cosmic litmus test for Planet 9's reality. These discoveries either strengthen the case for a hidden ninth planet or force scientists to reconsider whether the clustering they've observed is as meaningful as they believed. The object called the Goblin, officially designated 2015 TG387, provided one of the strongest confirmations of Planet 9's gravitational influence. Discovered in 2015 but not announced until 3 years later. After careful verification, the Goblin follows an orbital path that aligns perfectly with Planet 9 predictions. Its closest approach to the Sun brings it to about 65 times Earth's distance, still farther than any known planet in our solar system. Its farthest point carries it outward to nearly 2,300 times Earth's distance, venturing into realms where the Sun appears as just another star. Think of the Goblin as a cosmic messenger carrying urgent news from the outer darkness about the gravitational forces that shape its impossible path through space. Computer simulations clearly show that without Planet 9's influence, the Goblin's orbit should be chaotic and unstable, decaying over cosmic time. But with a massive ninth planet shepherding its motion, the Goblin's path becomes stable and predictable over millions of years. The discovery of Far Out, officially designated 2018 VG18, added another crucial piece to this cosmic puzzle. This mysterious object currently holds the record as the most distant known member of our solar system, orbiting at approximately 120 times Earth's distance from the Sun. While Far Out doesn't show the extreme orbital clustering of other Planet 9 candidates, its very existence proves that substantial objects can survive in the outer reaches where Planet 9 supposedly lurks. But not every new discovery supports the Planet 9 hypothesis, creating confusion in the astronomical community. The object designated 2018 VP1, nicknamed Dragonfly, follows an orbit that doesn't fit the clustering pattern at all. Its orbital orientation points in completely the wrong direction, and its path doesn't show the extreme elongation expected from Planet 9's gravitational influence. These non-conforming objects pose a serious challenge to the Planet 9 theory that keeps astronomers debating. If a massive planet is really shepherding objects in the outer solar system, why don't all distant objects show identical orbital characteristics? The discovery of even one object that clearly contradicts Planet 9's predicted influence could potentially undermine the entire hypothesis that has captivated the astronomical community. Some astronomers argue that these non-conforming objects actually strengthen the case for Planet 9 by providing a natural control group. According to this interpretation, Planet 9 only influences objects that venture into specific regions of space during their orbits. Some astronomers argue that these non-conforming objects actually strengthen the case for Planet 9 by providing a natural control group. Objects like Dragonfly that avoid these gravitational zones should show random orbital orientations exactly as observed. The mathematical odds of such precise clustering occurring through pure random chance have now dropped to less than 1 in several thousand, representing statistical evidence that would convince most scientists of a hidden cause. But the statistics also reveal troubling gaps in the data that keep skeptics questioning the entire Planet 9 hypothesis. Most of the clustering objects were discovered by the same research teams using nearly identical survey techniques and similar telescope systems. This observation bias might inadvertently create artificial clustering that has absolutely nothing to do with Planet 9's actual gravitational influence throughout the outer solar system. Recent studies have desperately attempted to address these legitimate concerns by carefully analyzing objects discovered by completely independent surveys, using entirely different search strategies and methodologies. The clustering signal remains remarkably strong even when potential observation bias is properly taken into account, but the statistical significance somewhat reduced compared to earlier, more optimistic estimates. The heated debate over alternative explanations for the clustering has forced astronomers to develop increasingly sophisticated methods for analyzing orbital data and accounting for subtle observational biases that might contaminate their results. As more mysterious objects are discovered and analyzed with greater precision, the cosmic jury continues deliberating on Planet 9's guilt or innocence. Planet 9's ultimate fate might have been decided by stellar neighbors that disappeared into the cosmic void billions of years ago, long before Earth even existed. The complete story of Planet 9 cannot be properly told without understanding the crowded stellar nursery, where our entire solar system was originally born. 4.5 billion years ago, our sun wasn't the isolated star we know today, peacefully burning in relative solitude. Instead, it was an active member of a bustling stellar community, where hundreds of young stars formed, lived, and interacted in violent ways that permanently shaped the fundamental architecture of planetary systems throughout the galaxy. In those incredibly chaotic early days, passing stars regularly ventured close enough to our developing solar system to dramatically disrupt planetary orbits through their immense gravitational influence. These stellar encounters, some approaching closer than the current distance to Pluto, could have been directly responsible for flinging Planet 9 into its current distant orbit, or even capturing it from another star system entirely through gravitational theft. Think of the early stellar cluster like a massive cosmic dance floor where partners constantly changed in an endless gravitational ballet. Stars would slowly approach each other across millions of miles, perform an intricate gravitational waltz that lasted thousands of years, then separate and move on to new partners in the cosmic crowd. During these prolonged encounters, entire planets could be stolen through gravitational capture, violently ejected into interstellar space, or dramatically relocated within their host systems to completely different orbital zones. Sophisticated computer simulations of these ancient stellar encounters reveal something shocking about early solar system formation. Close approaches between neighboring stars were not rare cosmic accidents or unusual events. Instead, they represented inevitable consequences of stellar formation occurring in dense clusters where hundreds of stars competed for gravitational dominance. The young sun likely experienced dozens of close encounters with neighboring stars during its first 100 million years of turbulent existence. The closest encounters could have approached within 50 times Earth's distance from the sun, bringing them close enough to completely reshape the entire outer solar system through gravitational disruption. During such dramatic encounters, the intense gravitational tug-of-war between two massive stars could easily fling planets weighing several times Earth's mass into highly elliptical orbits, or even eject them from the solar system entirely, sending them drifting alone through interstellar space. Recent studies suggest that these ancient stellar encounters might explain not just Planet 9's mysterious existence, but also several other puzzling features about our solar system's architecture that have confused astronomers for decades. The unusual orbits of objects scattered throughout the Kuiper belt, the dramatically tilted spin axis of Uranus that makes it roll like a ball instead of spinning like a top, and even the bizarre orbital characteristics of some of Jupiter's moons might all bear the invisible gravitational scars of ancient stellar encounters. The stellar influence theory makes specific testable predictions about Planet 9's physical properties that could be verified once it's finally discovered and studied. A planet that was displaced by stellar encounters should display chemical and isotopic signatures that reflect its original formation location, not its current position in the outer darkness. If Planet 9 formed closer to our Sun but was kicked outward by violent stellar encounters, its composition should resemble that of Uranus and Neptune, rather than the ice-rich objects currently found in the Kuiper belt. The precise timing of stellar encounters also matters crucially for understanding Planet 9's history. Most of our Sun's birth cluster dispersed within the first 100 million years, taking the disruptive stellar neighbors with them into the cosmic void. This means any major orbital disruptions, including Planet 9's ejection to its current remote orbit, must have occurred very early in solar system history. The dispersal of the birth cluster might have actually saved Planet 9 from complete ejection into interstellar space. Computer simulations clearly show that if stellar encounters had continued for longer periods, Planet 9 would likely have been expelled from the solar system entirely, becoming a rogue planet drifting alone through the galaxy. The stellar influence extends far beyond individual planet trajectories to affect the entire structure of the outer solar system. The same encounters that shaped Planet 9's orbit could have scattered countless smaller objects, creating the extended disk of debris that we observe today in the Kuiper belt and Oort cloud. Understanding stellar influences on planetary system evolution has become a crucial component of exoplanet research, as astronomers study how planetary systems around other stars might have been shaped by similar violent processes. The ghost of ancient stellar encounters continues to haunt our solar system leaving gravitational fingerprints that point toward a hidden world shaped by forces from the cosmic deep. The hunt for Planet 9 has evolved into a technological arms race between human ingenuity and cosmic darkness. Astronomers have completely abandoned the traditional approach of simply pointing telescopes at the sky and hoping to spot Planet 9 through luck or persistence. Instead, they've developed sophisticated strategies that combine multiple wavelengths of light, advanced computer algorithms, and even cutting-edge theoretical physics to track down our solar system's most elusive resident. The infrared approach represents one of the most promising new detection methods being developed. While Planet 9 reflects very little visible sunlight from its frozen surface, it might still be warm enough from its formation 4 billion years ago to emit detectable infrared radiation into space. Objects the size of Neptune retain internal heat for billions of years, glowing like cosmic embers in the darkness of space long after their formation. NASA's Wide Field Infrared Survey Explorer spacecraft has already systematically scanned most of the sky in infrared light. Scientists are carefully mining that enormous database for slow-moving objects that previous analyses somehow missed. The challenge lies in distinguishing Planet 9's incredibly faint infrared glow from the billions of background stars and galaxies that also emit heat radiation. Think of it like trying to spot a single warm coal scattered in a field completely full of campfires. The coal might be glowing steadily, but it's vastly outnumbered by brighter heat sources that can completely mask its presence. Advanced image processing techniques can digitally filter out known background objects, but Planet 9's signal might still be buried in statistical noise. The parallax method offers another promising detection strategy that doesn't require Planet 9 to be particularly bright, opening new possibilities for discovery. What if I told you that distant stars trillions of miles away could be the key to finally catching our solar system's most elusive ghost? Here's where things get absolutely mind-blowing. Those background stars might seem motionless to us, frozen like cosmic diamonds against the velvet darkness, but they're actually perfect landmarks for hunting down Planet 9. Picture this incredible cosmic dance. Earth swings around the sun like a massive pendulum, completing its orbital journey every single year. Every 6 months, we find ourselves looking at space from completely opposite sides of our orbit, like standing on different sides of an enormous room. Any object that belongs to our solar system will appear to shift slightly against those distant stellar backgrounds, creating what astronomers call parallax motion. It's exactly like closing one eye then the other, and watching your finger seem to jump back and forth against the wall behind it. This parallax technique becomes absolutely revolutionary when hunting for objects too dim to spot in single photographs. Scientists have mastered the art of stacking multiple images together, amplifying faint signals that would otherwise remain completely invisible in the cosmic darkness. Even if Planet 9 is too dark for our most powerful telescopes to see directly, its subtle dance against the cosmic backdrop might finally give away its secret location. The beauty of this method lies in its reliability. Unlike other detection techniques that depend on lucky timing or perfect conditions, parallax works consistently for any solar system object, regardless of how faint or distant it might be. The only requirement is patience and precision, waiting those crucial 6 months for Earth to reach the opposite side of its orbit, then comparing images with microscopic attention to detail. But here's where detection strategies venture into truly wild territory. Imagine Planet 9 playing the ultimate game of cosmic hide-and-seek by sliding in front of distant stars, temporarily blocking their light like a celestial eclipse. This occultation method sounds almost too good to be true, but it's based on solid astronomical principles that have worked for detecting other objects before. The chances of witnessing such an occultation are astronomically small, literally like finding a needle in a cosmic haystack. But networks of small telescopes monitoring thousands of stars simultaneously have turned this impossible task into a waiting game with real possibilities. These automated sentinels scan the sky night after night, hoping to catch our hidden giant red-handed during one of these stellar vanishing acts. The real game changer has been artificial intelligence storming into astronomy like an army of digital detectives. These machine learning systems have completely transformed how we hunt for planets by analyzing millions of astronomical images with superhuman speed and precision that leaves human astronomers in the dust. These AI systems are trained like cosmic bloodhounds, learning to recognize the subtle fingerprints of planetary motion by studying thousands of known asteroids and comets. They analyze how these objects move, the patterns they create, and the telltale signs that distinguish genuine solar system members from background noise or instrumental artifacts. Once trained, these algorithms become astronomical archaeologists, diving deep into decades of archived observations and scanning through data that would take human researchers lifetimes to analyze. They're searching for similar patterns that human eyes might never notice, subtle correlations that could reveal the presence of undiscovered worlds lurking in our solar system's shadows. The sophistication of these AI systems continues advancing at breathtaking speeds. Modern algorithms can process data from multiple telescopes simultaneously, cross-reference observations taken years apart, and even predict where to look for objects based on gravitational models. They've become so refined that they can distinguish between genuine planetary signals and false positives caused by instrumental glitches, atmospheric distortions, or cosmic ray hits. Think about the most exotic detection method yet conceived: gravitational microlensing. This technique sounds like pure science fiction, but it's based on Einstein's most mind-bending predictions about how gravity actually works in our universe. If Planet 9 ever drifts directly between Earth and a background star, something absolutely magical happens. The planet's gravity would bend that star's light like a cosmic magnifying glass, focusing the stellar radiation and making the star temporarily appear brighter from our perspective. It's as if the universe itself becomes a telescope, using gravity as its lens. The specific way this brightening occurs would reveal Planet 9's mass and distance like a gravitational fingerprint. The duration tells us about the planet's speed and orbital motion. The intensity reveals its mass. The exact shape of the brightening curve provides clues about its size and composition. It's like reading a cosmic biography written in light itself. Some research teams are even exploring whether Planet 9's gravitational pull might betray its location through tiny deviations in spacecraft trajectories. This approach turns our distant space probes into unwitting Planet 9 detectors, monitoring their paths with ultra-precise tracking systems that can detect course corrections smaller than the width of a human hair. When spacecraft like Voyager, New Horizons, or the Pioneer probes travel to the outer solar system, they follow precisely calculated trajectories based on the known gravitational influences of the Sun and major planets. Any deviation from these predicted paths could indicate the gravitational tug of an unknown massive object. The most ambitious hunting strategies involve coordinating multiple telescopes worldwide to simultaneously monitor different sections of the predicted search zone. This global approach maximizes our chances of catching Planet 9 during those brief moments when it might be detectable, creating a planetary surveillance network that operates around the clock. These coordinated efforts represent international collaboration at its finest, with research teams sharing data, coordinating observations, and pooling resources to tackle one of astronomy's greatest mysteries. Yet even with all this technology and cooperation, success might ultimately depend on revolutionary new instruments that haven't even been invented yet. Now here's where mathematics becomes more convincing than any telescope image could ever be. The case for Planet 9 has evolved from interesting coincidence to statistical near certainty, reaching levels of mathematical proof that approach absolute scientific certainty. Statistical significance serves as the crucial dividing line, separating curious observations from revolutionary discoveries that change our understanding of the universe. When only 6 distant objects showed mysterious orbital clustering, skeptics could reasonably argue for cosmic coincidence. Random chance could potentially explain such a small sample. But as more distant objects have been discovered following identical patterns, the probability of random chance has plummeted to levels that strain scientific credibility. We're not talking about 7 or 8 objects anymore, but dozens of distant worlds all following eerily similar orbital paths that seem to point toward the same invisible gravitational shepherd. Imagine statistical evidence like a cosmic courtroom where each new clustered object serves as another witness, testifying to Planet 9's existence. Every computer simulation requiring a massive 9th planet to explain observations becomes additional forensic evidence, pointing toward the same inescapable conclusion. Current statistical significance exceeds 4 sigma in scientific terminology, meaning random chance, odds are less than 1 in 15,000. Most scientific fields consider 3 sigma strong evidence, while 5 sigma constitutes mathematical proof. Planet 9 is rapidly approaching that threshold, where denial becomes statistically untenable and scientifically irresponsible. Imagine discovering that your supposedly unique family actually follows patterns common to families everywhere across the globe. That's exactly what Planet 9 would do for our solar system, transforming us from cosmic oddball into a perfectly normal example of how planetary systems naturally develop throughout the universe. This revelation would fundamentally reshape our understanding of planetary formation and evolution on a galactic scale. The orbital characteristics predicted for Planet 9 match patterns observed in exoplanet systems with stunning precision. Throughout our galaxy, many stars host super-Earths and mini-Neptunes following highly elliptical orbits that carry them far from their host stars during parts of their cosmic journeys. These distant, eccentric orbits initially puzzled astronomers until they realized such strange paths could result from complex gravitational interactions with other planets, or even nearby stars during the chaotic early phases of system formation. Planet 9's predicted orbit, highly elliptical and tilted relative to our solar system's main planetary plane, fits perfectly with theoretical models explaining how planetary systems evolve through billions of years of gravitational interactions. Its existence would provide astronomers with a local laboratory for studying processes that shape planetary architecture throughout the galaxy, offering unprecedented insights into cosmic-scale phenomena. The formation scenarios proposed for Planet 9 have direct applications to exoplanet studies that could revolutionize our understanding of planetary birth and migration. If Planet 9 formed closer to the Sun during our solar system's violent youth, and subsequently migrated outward through gravitational encounters with Jupiter and Saturn, it would represent a textbook example of planetary migration, one of the most important processes governing exoplanet evolution throughout the universe. Planetary migration explains countless puzzling features of exoplanet systems discovered by space telescopes, including hot Jupiters that orbit incredibly close to their stars despite forming much farther away, and planetary systems with architectures completely unlike our own solar system. Planet 9 would provide the first detailed case study of migration occurring within our own cosmic neighborhood, allowing astronomers to test and refine their migration models with unprecedented precision and detail. The detection techniques developed specifically for Planet 9 hunting are already being applied to the broader search for exoplanets around distant stars. Advanced methods for identifying faint, slowly moving objects in astronomical images have dramatically improved our ability to detect distant exoplanets through direct imaging techniques that capture actual light from these alien worlds. Statistical techniques originally designed for analyzing orbital clustering patterns are now being used to identify complex multiple planet systems around other stars, revealing the hidden architecture of distant solar systems. Perhaps most importantly, Planet 9 could provide crucial insights into planetary system stability over geological timescales. Sophisticated computer simulations suggest that planetary systems with architectures similar to ours, including a distant super-Earth, acting as a gravitational guardian like Planet 9, might remain stable over billions of years compared to systems lacking such outer planetary sentinels. If these simulations prove correct, the implications for astrobiology and the search for habitable exoplanets would be profound and far-reaching. Stable planetary systems are significantly more likely to maintain the consistent environmental conditions necessary for life to evolve, flourish, and develop complexity over the immense timescales required for biological evolution. Planet 9 might represent a crucial component in making our solar system particularly suitable for supporting complex life forms like ourselves. The study of Planet 9 has already advanced our understanding of how gravitational interactions sculpt planetary systems, how planets migrate during their tumultuous formation periods, and how planetary architectures evolve over cosmic timescales spanning billions of years. These insights will prove invaluable as astronomers study the thousands of exoplanets waiting to be discovered in the coming decades through next-generation space missions and ground-based surveys. But here's the reality that makes this decade absolutely crucial. The next 10 years will either definitively discover Planet 9 or prove beyond reasonable doubt that it doesn't exist. There's no middle ground left in this cosmic detective story. The technological revolution sweeping through astronomy is approaching a critical tipping point that will resolve the Planet 9 mystery one way or another with mathematical certainty. Revolutionary new telescopes, advanced detectors, and unprecedented search strategies are converging to create detection capabilities that dwarf anything available to previous generations of planet hunters. We're entering an era of astronomical discovery, unlike anything in human history. The Vera C. Rubin Observatory in Chile represents the most ambitious ground-based survey ever conceived by human minds. Beginning full operations in the mid-2020s, this technological marvel will photograph the entire visible sky every few nights with unprecedented depth, precision, and consistency. Its giant digital camera captures images containing over 3 billion pixels, creating a time-lapse movie of the cosmos that reveals anything moving against the background stars. Think of the Rubin Observatory as a cosmic security camera with perfect memory and infinite patience, never blinking, never forgetting, never overlooking even the faintest moving object. It will automatically detect and track every moving object brighter than 25th magnitude across the entire southern sky. If Planet 9 exists anywhere within its detection limits, the Rubin Observatory should find it within its first few years of systematic operations. The Nancy Grace Roman Space Telescope, launching in the mid-2020s, will extend this search into infrared wavelengths, where Planet 9 might be most easily detectable. Its position high above Earth's turbulent atmosphere will provide crystal-clear images completely free from the distortions and interference that limit ground-based telescopes. The Roman telescope's exceptional infrared sensitivity could detect Planet 9's faint heat signature at vast distances, where reflected sunlight becomes completely undetectable. But the most exciting developments might emerge from completely unexpected directions that push the boundaries of detection science. Artificial intelligence algorithms, trained on the distinctive signatures of planetary motion, are becoming sophisticated enough to identify Planet 9 even in decades-old archival images where human analysts completely missed its presence. These digital archaeologists are systematically excavating vast databases of astronomical observations, searching for faint signals that earlier searchers overlooked due to technological limitations. The breakthrough might come from gravitational wave detectors, instruments originally designed to detect ripples in spacetime from colliding black holes billions of light-years away. If Planet 9 has a large moon or binary companion, their orbital dance might create detectable gravitational wave signals that could pinpoint the planet's location without requiring any electromagnetic radiation whatsoever. Even interplanetary spacecraft are becoming sensitive enough to detect Planet 9's gravitational influence through precision trajectory analysis. The Parker Solar Probe, New Horizons, and Voyager spacecraft all carry instruments capable of measuring microscopic deviations in their carefully calculated paths. Coordinated analysis of multiple spacecraft trajectories might triangulate Planet 9's position through pure gravitational forensics. The James Webb Space Telescope, already revolutionizing our understanding of the early universe and distant galaxies, might accidentally stumble across Planet 9 while conducting deep infrared surveys of seemingly empty regions of space. Its incredible sensitivity and unprecedented resolution could detect Planet 9 as a slowly moving infrared source, distinguishing it from stationary background objects through precise measurements of its position, brightness, and color. The convergence of these revolutionary technologies creates a detection network so comprehensive and sensitive that Planet 9 would need to be extraordinarily well hidden to avoid discovery much longer. If it exists within the mass and distance ranges predicted by current theoretical models, multiple independent detection methods should find it within this decade. But if Planet 9 remains undetected despite these unprecedented technological advances, that absence would become just as scientifically significant as a positive detection. The null result would force astronomers to fundamentally reconsider basic assumptions about planetary formation, gravitational dynamics, and the architecture of our solar system. The stage is perfectly set for the final act in one of astronomy's greatest detective stories, and the resolution is finally within reach. The hunt for Planet 9 has shattered our comfortable assumptions about our cosmic neighborhood, revealing that our solar system still harbors profound secrets lurking in the endless darkness beyond Neptune's orbit. What began as a handful of mysterious orbital patterns has evolved into one of the most compelling detective stories in modern astronomy, transforming our understanding of how planetary systems actually work. From those first puzzling orbital alignments that whispered of an invisible gravitational puppet master controlling distant worlds, to the sophisticated computer simulations that now map its theoretical influence with stunning precision, we followed mathematical breadcrumbs through the cosmic darkness toward what could represent the most significant planetary discovery since Neptune shocked the world in 1846. The evidence has undergone a remarkable transformation, evolving from curious coincidence into compelling proof that something massive is orchestrating the outer solar system's gravitational symphony from the shadows. This isn't just about finding another rock floating in space. What if a Planet 9 turns out to be a super-Earth exile banished from the inner solar system by gravitational warfare between ancient giants, a rogue world captured from the gravitational embrace of another star during a close stellar encounter, or something even more exotic that challenges our current theories? Its discovery would fundamentally revolutionize our understanding of planetary formation and solar system evolution throughout the universe. We would learn that our cosmic neighborhood is far more dynamic, violent, and chaotic than we ever dared imagine, shaped by colossal forces operating on timescales that completely dwarf human history and civilization. The discovery would reveal that planetary systems are living, breathing entities that continue evolving and changing over billions of years, not the static, unchanging arrangements we once believed them to be. But Planet 9 represents something far deeper and more profound than simply adding another world to our solar system's census. It embodies the incredible power of human curiosity to detect the completely invisible, to read gravitational signatures like cosmic fingerprints left by unseen worlds, and to wield mathematics as a precise tool for exploring the universe's most hidden architectural secrets. The searchers pushed telescope technology to its absolute limits, forcing engineers and scientists to develop entirely new techniques for finding incredibly faint objects against the overwhelming brightness of background stars. It has created computer simulations so sophisticated they can fast forward through billions of years of planetary evolution in mere hours, revealing the complex gravitational dance that shapes solar systems across cosmic time. The hunt for Planet 9 has also perfectly demonstrated the intensely collaborative nature of modern science, where research teams scattered around the world freely share data, meticulously compare results, and build upon each other's discoveries, even while competing fiercely for the ultimate prize of first detection. This global cooperation shows how modern astronomy has become a truly international endeavor that transcends borders, politics, and individual ambitions. The search beautifully illustrates how statistical analysis can transform seemingly random astronomical observations into mathematical certainty that approaches scientific proof. It demonstrates how indirect evidence, like gravitational footprints and orbital clustering patterns, can become just as compelling and convincing as directly photographing a planet with our most powerful telescopes. Perhaps most remarkably, this cosmic detective story has demonstrated that major paradigm-shifting discoveries about our own solar system remain absolutely possible, even in the 21st century. In an incredible age when Mars rovers analyze alien rocks with laboratory precision, space telescopes peer into the earliest moments of cosmic history, and we've detected thousands of exoplanets orbiting distant stars. We've learned that profound mysteries still lurk literally in our own cosmic backyard. The outer solar system remains largely unexplored territory, a vast frontier where new worlds await discovery by the next generation of astronomical instruments. Beyond Planet 9, there could be entire populations of distant objects, maybe even multiple unknown planets, hiding in the darkness at the very edge of our sun's gravitational influence. The next decade absolutely promises to resolve the Planet 9 mystery one way or another, bringing this decades-long investigation to its dramatic conclusion. Advanced telescopes like the Vera Rubin Observatory and Nancy Grace Roman Space Telescope Revolutionary artificial intelligence algorithms capable of processing millions of images and completely new detection techniques are rapidly converging to create discovery capabilities that will either definitively find our hidden ninth planet or prove beyond any reasonable doubt that it simply doesn't exist. We genuinely stand at the threshold of answering one of the most compelling and important questions in contemporary planetary science. The technological tools finally exist to solve this mystery that has captivated scientists and space enthusiasts worldwide for over a decade. But here's what makes this story even more fascinating. Regardless of whether Planet 9 is ultimately found hiding in the darkness or completely ruled out by exhaustive searches, the investigation has already fundamentally transformed our understanding of how planetary systems evolve, migrate, and interact over cosmic timescales. We've learned that our solar system is far stranger, more dynamic, and more violent than we ever imagined possible. The search has revealed that planetary migration is a common, perhaps universal process that reshapes solar systems throughout their lifetimes. It's shown us that gravitational interactions between planets can scatter worlds across vast distances, ejecting some into interstellar space while capturing others from neighboring star systems. We've discovered that the outer regions of planetary systems are active, evolving environments where cosmic archaeology can reveal the violent history of planetary formation. These insights extend far beyond our own solar system, providing crucial context for understanding the thousands of exoplanet systems discovered around other stars. The techniques developed for hunting Planet 9 are already being applied to detect and characterize distant exoplanets, creating a feedback loop where solving local mysteries advances our understanding of planetary systems throughout the galaxy. What other cosmic secrets are hiding in the darkness, waiting patiently for the next generation of planet hunters to uncover them with even more sophisticated tools and techniques? Could there be multiple unknown planets lurking beyond Neptune? Might there be entire asteroid belts or comet populations we've never detected? Are there captured interstellar objects hiding among the solar system's permanent residents? The search for Planet 9 has taught us that our solar system still holds incredible surprises, that major discoveries remain possible, and that the universe's capacity to amaze us remains absolutely unlimited. Every time we think we understand our cosmic neighborhood completely, new mysteries emerge to challenge our assumptions and expand our perspectives. The hunt continues, and the next chapter in this incredible story could be written at any moment. Whether Planet 9 emerges from the darkness to take its place among the solar system's family of planets, or whether its absence teaches us equally valuable lessons about planetary formation and evolution, we're witnessing one of astronomy's greatest detective stories unfold in real time. If you're fascinated by the cosmic detective work that's fundamentally reshaping our understanding of the solar system and revealing the hidden architecture of planetary formation throughout the universe, make sure to subscribe for more astronomical mysteries that challenge everything we thought we knew about our place in the cosmos. Hit that notification bell so you never miss the latest groundbreaking discoveries from the final frontier, because in astronomy, the next world-changing discovery could happen at any moment.